Welcome back. Last episode, we squeezed a whole system of linear equations into a single augmented matrix. Today, we learn the algorithm that turns that matrix into answers, and it works on every linear system without exception, Gaussian elimination. The plan is this. We start with three simple moves called elementary row operations, each one reversible and each one leaving the solutions untouched. We use those moves to march the matrix into a staircase shape called row echelon form, and then a cleaner version called reduced row echelon form. Along the way, we will meet pivots, the leading entries of that staircase, and free variables, the unknowns we are allowed to choose. Then, we read off the answer by back-substitution, working from the bottom row upward. And we will see how a single impossible row instantly tells us the system has no solution. One algorithm that handles a unique solution, infinitely many, or none. Let's begin. Everything rests on three moves you are allowed to make on the rows of the augmented matrix. Each row is an equation, so think of these as legal ways to rewrite the equations. The first move is to swap two rows, just reorder two equations. The second is to scale a row, multiplying every entry in it by a non-zero constant, that is multiplying an equation through by a non-zero number. The third, and the workhorse, is to replace a row by itself plus a multiple of another row, that is adding one equation to a multiple of another. Two facts make these moves safe. First, every one of them is reversible. You can swap back, divide by the constant, or subtract off what you added. Second, and most important, none of them changes the solution set. The system you get afterwards has exactly the same solutions as the one you started with. So we may apply these operations as often as we like, in any order, confident that we are simplifying the numbers without ever disturbing the answer. The goal of the forward phase is a shape called row echelon form. A matrix is in row echelon form when three conditions hold. First, any rows that are entirely zero sit at the very bottom. Second, in each non-zero row, the leading non-zero entry, the first non-zero number you hit scanning left to right, which we call the pivot, lies strictly to the right of the pivot in the row above it. Third, every entry directly below a pivot is zero. Look at the shape on the slide. The pivots, marked as solid squares, step down and to the right like a staircase, and underneath each pivot there is nothing but zeros. The stars stand for entries we do not care about, they can be anything. This staircase structure is what makes the system easy to solve, because the bottom rows involve the fewest unknowns. We reach this form by using the lowest pivot to clear out everything beneath it, then moving up and to the left one column at a time. We can polish row echelon form one step further into reduced row echelon form, often abbreviated RREF. It asks for two extra things. First, every pivot must equal 1, a leading one, which we arrange by scaling each pivot row. Second, every entry above a pivot, not just below, must be 0, so that each pivot stands completely alone in its column. Look at the example. Each pivot is a 1, and its column is otherwise all zeros. Getting there is just Gaussian elimination followed by clearing upward as well as downward, a version sometimes called Gauss-Jordan elimination. Two remarks. Unlike row echelon form, which can look slightly different depending on your choices, the reduced form is unique. Every matrix has exactly one RREF. And the payoff is that once a system is in reduced row echelon form, the solution can be read straight off the page with essentially no arithmetic left to do. The hard work is finished, the answer is just sitting there. Once the matrix is reduced, the columns to the left of the bar split into two kinds, and this is where we actually count solutions. A column that contains a pivot corresponds to a basic variable, one that is pinned down by the equations. A column with no pivot corresponds to a free variable, one you are allowed to set to anything, a dial to turn. From this split, everything follows. If every variable column has a pivot and the system is consistent, there are no free variables and you get exactly one solution. If the system is consistent but has at least one free variable, you get infinitely many solutions, one for each choice of the parameters. And there is a special warning sign if a pivot ever appears in the very last column, the one to the right of the bar, the system is inconsistent and has no solution at all. Each free variable adds one dimension to the solution set, one free variable gives a line of solutions, two give a plane, and so on. Here is how you extract the answer. The method is called back-substitution because you work from the bottom up. Once the matrix is in echelon form, the bottom pivot row involves the fewest unknowns, so start there and solve for its variable. For instance, if the bottom row reads 2z equals 6, then z is 3. Now move up one row and substitute that known value in, which lets you solve for the next variable and continue climbing until every variable is found. Now the crucial special case. Suppose row reduction produces a row that is all zeros to the left of the bar but has a non-zero number on the right. That row claims 0 equals some non-zero number, a flat contradiction. The moment you see it, you can stop. The system is inconsistent and has no solution. Be careful to distinguish it from a row of all zeros, including a 0 on the right. That one just says 0 equals 0, which is harmlessly true. It is a redundant equation, and it is the signal of a free variable, not of a contradiction. Let's watch the reduction happen. On the left is a full augmented matrix, 3 rows, 4 columns, the bar before the last column, and numbers scattered everywhere with no structure. In the middle snapshot, we have used the top left entry, circled in gold, as our first pivot, to clear the column below it. Those freshly created zeros are shaded blue, so you can see the first column is now a pivot on top and zeros beneath. On the right, the process is finished, a clean staircase. 3 gold-circled pivots descend from upper left to lower right, and below each pivot the entries are all 0, filling in the lower triangle. That descending staircase, with a triangle of zeros beneath it, is row echelon form. Notice the rhythm: pick a pivot, clear everything below it, move down and to the right, repeat. Each step uses the third row operation, adding a multiple of the pivot row to the rows beneath, to knock out one column at a time. Here are the 3 outcomes, each read directly off a reduced matrix. At the top, the unique solution case. Every variable column carries a gold pivot. The left block is the identity, and the numbers past the bar are the answer itself. 1 value per variable, no choices to make. In the middle, the infinitely many case, 1 variable column, highlighted orange, has no pivot. That column is a free variable, a parameter you may set however you like, and the bottom row of all zeros confirms a redundant equation rather than a contradiction. Every choice of the parameter gives another solution, so there are infinitely many. At the bottom, the no solution case, the bottom row is all zeros to the left of the bar but carries a bold red non-zero entry to the right. That row insists 0 equals a non-zero number, which is impossible, so the system is inconsistent. Pivot in every variable column means 1 solution, a free column means infinitely many, an impossible row means none. Let's run the full algorithm once. We have x plus y plus z equals 6, y plus 2z equals 11, and 2x plus z equals -1. Write the augmented matrix. The first 2 rows already have a clean start, so we attack the third. Replace row 3 by row 3 minus 2 times row 1, which kills the 2 in the bottom left. That turns the bottom row into 0, -2, -1, with -13 on the right. Now replace that row by itself plus 2 times row 2, clearing the second column too. The bottom row becomes 0, 0, 3, with 9 on the right. A clean staircase. Now back. Substitute from the bottom. The last row says 3z equals 9, so z is 3. Move up, the middle row is y plus 2z equals 11, and with z equal to 3, that is y plus 6 equals 11, so y is 5. Move up again, the top row is x plus y plus z equals 6, that is x plus 5 plus 3 equals 6, so x is -2. The unique solution is -2, 5, 3. Now, a system with a free variable. We have x plus 2y plus z equals 4, and 2x plus 4y plus 3z equals 9. Write the augmented matrix and clear the first column, replace row 2 by row 2 minus 2 times row 1. The bottom row becomes 0, 0, 1 with 1 on the right. Look at the pivots. There is a pivot in column 1 and a pivot in column 3, but column 2 has no pivot, so y, the variable for column 2, is free. We set it to a parameter t. Now read the rows. The second row says z equals 1. The first row says x plus 2y plus z equals 4. Substituting z equals 1 and y equals t gives x equals 4 minus 2t minus 1, which is 3 minus 2t. So the complete solution is the triple 3 minus 2t, t, 1, as t ranges over all real numbers. That is a line of solutions in space. 1 free parameter, 1 dimension, infinitely many points. Finally, a system that has no solution, so we can see the impossible row in action. We have x plus y plus z equals 2, y plus z equals 1, and x equals 2. Write the augmented matrix. Clear the first column using the top row, replace row 3 by row 3 minus row 1. The bottom row becomes 0, -1, -1 with 0 on the right. Now clear the second column, replace that row by itself plus row 2. Adding 0, 1, 1, 1 to 0, -1, -1, 0 gives 0, 0, 0 with 1 on the right. Read that bottom row as an equation. 0x plus 0y plus 0z equals 1. That is, 0 equals 1. That is impossible. No values of x, y, and z can make it true. The system is inconsistent, and we stop. There is no solution. Notice how the algorithm detected this automatically. We did not need any geometric insight, just the appearance of that one contradictory row. A bit of history closes the loop from last episode. The Chinese classic The 9 Chapters on the Mathematical Art from around 200 BCE already solved systems by juggling an array of rod numerals on a counting board, row reduction in all but name, more than 2,000 years ago. Around 1670, Isaac Newton wrote up a general elimination procedure for systems of equations. In the 1810s, Carl Friedrich Gauss applied systematic elimination to enormous least squares computations for astronomy and land surveying, and the method came to bear his name. And in 1888, the geodesist Wilhelm Jordan popularized carrying the reduction all the way to the fully reduced form, which is why pushing to reduced row echelon form is often called Gauss-Jordan elimination. So the recipe you learned today is the same array juggling humans have done for 2 millennia, sharpened into a guaranteed mechanical algorithm. Let's recap. Gaussian elimination uses 3 elementary row operations, swapping 2 rows, scaling a row by a non-zero number, and replacing a row by itself plus a multiple of another. Each is reversible, and each preserves the solution set. With them, we drive the matrix to row echelon form, a staircase of pivots with zeros below, and then to reduced row echelon form, where every pivot is a one alone in its column, a form that is unique. Pivot columns give basic variables, columns without a pivot give free variables, which become parameters. We read the answer by back-substitution, working from the bottom up. And the outcome count is automatic. A pivot in every variable column gives one solution, a free variable gives infinitely many, and an impossible row reading 0 equals a non-zero number means no solution. Next episode, we run these very same row operations alongside the identity matrix to compute the inverse of a matrix. The same machinery, a new payoff. Today we learned Gaussian elimination, the algorithm that solves any linear system. It rests on 3 elementary row operations: swap 2 rows, multiply a row by a non-zero number, and add a multiple of one row to another. Each of these is reversible and none of them changes the solution set, so we may apply them freely. Using them, we drive the augmented matrix into row echelon form, a staircase where each leading non-zero entry, called a pivot, sits strictly to the right of a pivot in the row above, and every entry below a pivot is 0. Pushing further to reduced row echelon form makes every pivot a 1 with zeros both above and below it. Then the solution simply reveals itself. The columns that contain pivots correspond to basic variables. The columns without pivots correspond to free variables, which we set as parameters. Reading the equations from the bottom up, back-substitution expresses every solution. If a row ever reads 0 equals a non-zero number, the system is inconsistent and has no solution. One row contradiction means none, a free variable means infinitely many, a pivot in every variable column means exactly 1. Next episode, we run these same operations to compute the inverse of a matrix. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching, see you in the next one.